Okay, so good morning. My talk today is going to be a little bit different than what I usually do. I usually always come here and talk about meteors. But today I'm going to talk about space debris and a little bit about the synergy between our two communities. So my topic at the institute where I work is actually, I would title it Meteors and Space Objects. So that includes meteors and meteoroids, and near-Earth objects and comets, but also artificial resident space objects. And it might seem like the odd one out in this trio, but there's actually a lot of synergy. So in the end, I actually end up spending about 50-50 of my time on artificial space objects and natural objects. So I would just a quick sort of overview of these two populations. So I would call them adjacent and slightly overlapping. They have a few similarities, but they're very adjacent. I wouldn't call them like very similar. For meteoroids, like you know, they have high entry velocities, vast mass range, very small sizes, typical composition. You get deep trajectories into the atmosphere, and it's like de-influx into our atmosphere. Like that's our mass input. And it's a steady-ish population like we just heard. For artificial space objects, it's just below the limit because the typical orbital speed in LEO is 8 kilometers per second. The mass range is slightly bigger because we tend to launch big things like satellites. And it's like very non-natural composition. It's like everything from batteries and lithium to alloys and aluminium and all of these kinds of things. And also because they're in orbit, they have very shallow trajectories. And still a small influx. That still is an important word in that sentence, because there are massive changes ongoing to this population. But artificial space objects are not just active satellites, the one we actually launch and use. They're actually space debris as well. So I want to show this one. This is from the ESA movie Time to Act, and this is an animation of the master model. It's one of the models that ESA develops. So up there, you see that there's, let's see, this is the pointer, 34,000 objects. That is about 10 centimeters. When we go down to 1 centimeter, we get 900,000 objects. When we go down to 1 millimeter, it's like 128 million. And then, well, this size range is purely models as well, but like 2,000 billion when it goes up. So we have a lot of stuff already. And this is, I think, yeah, 2020 model. And this 2020 number is also an important number because we're going to see that a little bit more. So the composition of this is like it's space debris, everything from launch vehicles to rocket bodies. We have fragmented and destroyed spacecraft, non-functional objects. So you launch a satellite and then it stops working. You just leave it there. That's also debris. Ablated and lost debris. So things like paint flakes, nuts and bolts. Something we always mention when we talk about this is one of the Swedish astronauts, I think, dropped a screwdriver or something when he did a walk. So he gets to hear that every time he talks about this topic. Yeah. And weirdly enough, also like nuclear reactor cooling is a major component you have to include in these models to get it working. Because in like the Cold War time things, they launched a lot of nuclear reactors into space. And then when they shut out, they just opened up the cooling vats and went like, okay, let's release all the cooling into space. And that's apparently a significant part of the space debris population. So here we have this nice picture, and here we have this 2020. And I wanted to sort of show you that, yeah, things are kind of escalating at the moment. So this is number of objects. This is the payload launch traffic. This is how much more stuff we put into orbit, and we have like a reasonable number. This is like what's going on right now. We're just massively increasing the number of objects we're putting into space, and we are also actually seeing a really big increase in the number of reentries. So this is all in the ESA Space Environment Report 2025. They release one of these reports every year. So if you're interested, you can go there and look at it every year and see. So just to give you a sense here, I wanted to do some back of the envelope, like mega constellation calculations. So the plan for Starlink right now is to put between 12,000 and 34,000 satellites into orbit. That's like their current plan. That's what they need for their coverage. If you download some of the technical specs of their satellites, you can see in some obscure place, I had to look hard for this. It's like the design lifetime is 5 years. Okay. So I just went up and looked, okay, so the V1 is like 260 kilograms, the V2 Mini is 800. So let's assume that they're going to use the V2 Mini. That means that they're going to have to launch between 2,400 and 6,900 satellites per year to maintain this constellation. That also means that the same number is going to deorbit because they have a design lifetime of 5 years. That's like 2,000 to 5,000 tons per year of mass going up and down. That's like 5 to 15 tons per day for one mega constellation. And as we've heard, like ranges of natural input varies from, yeah, let's say most recent reports land around 40 tons per day. So, I mean, that's a significant percentage, which is a little bit frightening when you think that this is just one mega constellation and like people are not going to stop. So yeah, we're heading somewhere. Let's see where we are actually heading. And the current number surprised me a bit. There's 8,000 right now. So they gotten like pretty far in this. But then we have the question like how much actually gets injected into the atmosphere. The current sort of paradigm is designed for demise. So you design satellites to actually burn up in the atmosphere. So we have this anthropogenic input into the atmosphere. And there's this great paper by Leonard from 2021. I recommend you look at it. But they did calculations basically of how much is actually input into the atmosphere. So today, and these are in the percentages relative to the natural input. So today we're like, I think 1% in atomic and like 7% in aerosol, and total is like 3. So, okay, but if we take, these are different scenarios for developing of the amount of launches and constellations and everything. So this is like a nominal scenario, and this is like a mega constellation type-ish. Lots of everyone doing it scenario. And we get like very high in the mass input. And they also did element-wise injections in this paper, so they can actually compute like how much of each element we are contributing with this. So if you're interested, go have a look at that. So we know why to care about satellites. We use satellites all the time. Why should we care about space debris? Well, okay, space debris is also very important. Like everyone needs to know about gram aluminum sphere that impacted this slab at like 6.8 kilometers per second. Compared to typical collision velocity, like 8 to 12 kilometers per second in orbit. So yeah, if this is the result of a 1 gram aluminum sphere, like you don't want to be hit by anything in orbit. So even the small stuff matters. Okay, so that's sort of a quick intro to where we stand, what's sort of going on. What we need now is more observation. So we need more observations of both satellites. Yeah, and we've been saying more observation like this entire meeting, right? So surprise, surprise. But we need more observations of things while they're in orbit. We need better tracking of objects. We also need more observation during reentry. This is really important. Current instrumentation have sort of a hard time keeping up because there's so many objects. And also we need to observe smaller sizes. Typically, we only get down to like 10 centimeters. And you saw like what the 1 gram object did. So we need to get down smaller. And we need to understand the atmospheric impact of reentry, because we know that stuff is getting injected into the atmosphere, but we are not entirely sure how, in what form, what chemistry it does to our atmosphere, and how it's going to work when we scale up. So I would say there are lots of synergies between the Meteor community and the space safety, space debris community. So both in terms of ablation physics, because I mean, we do this. I mean, ablation physics is our jam. That's what a Meteor is. Even though the range is a bit different, we have all the expertise from the Meteor community, and I think we can do a lot. The same with the atmospheric chemistry. You can't really do atmospheric chemistry unless you know about the natural input. So all of these people who know atmospheric chemistry, they need to go and look at this artificial input to actually figure it out. And we're on the way. So there's actually a new workshop on this topic. So I thought I would sort of plug this here. We had the first one last year in ESTEC in 2024, and it was titled Understanding the Atmospheric Effects of Spacecraft Reentry. And the next one is next week in ESTEC. So if you're interested, you can go and have a look at the list of all the talks. I'm going to talk there, and I'm going to do the reverse of what I'm doing here. So here I'm talking about space debris, and there I'm going to talk about the natural input so that they get a sense of our community. And there's probably going to be one next year. So if you find this interesting and think you can assist, have a look out for the third installment of this. Okay, and then where I think everyone here can immediately find synergies with this community is in observations. So we see, like this is the typical way we observe meteors, right? We have a radar, it can reflect off the head or the trail. We have camera systems that observe the light. Well, I just replaced this with a satellite, and it's surprisingly similar, only the thing is that it doesn't emit its own light, we have the sun. So it's like with most instrumentations we are using for meteor studies, we can also see these things. So I'm just going to give a bunch of examples now to finish off. For example, the iSCAT radars. These are like one of the radar systems that I've been using a lot. Here is a nice video of one of the dishes. It's been contributing to meteor research since before I even started PhD. But it has also been one of the main data sources for calibrating the ESA space debris environment model. Because we can actually measure space debris that are very small with this. So the statistics from those measurements have helped calibrate this model. That's a really nice synergy. We can do both types of research with this instrument. One of the things that I was doing with this, when, let's see, when Russia did its anti-satellite test in 2021, they destroyed their own satellite, created a huge amount of debris. So we immediately went and scheduled observations with the iSCAT radars. And the summary of those observations are also in this publication. But basically, we saw the debris cloud. So this was, again, a really nice synergy, I think. It's very similar signal processing as we do with meteors. It's very similar data analysis. So here, this is like the typical background. And this blob was not there when we looked before. So this was obviously from the explosion. We have also been looking at using our aurora cameras to see if they can be used for doing space debris tracking. So here is an example. Now, if you look over here, you can see a small object moving. It's going to cycle again. So what these cameras are doing is continuously changing filter and looking at like one particular wavelength with a very narrow band. And in some of the wavelengths, you can actually see object. And these are very light sensitive cameras because they're supposed to look at the aurora. So we used this and we actually managed to do orbit determination. So we saw a bunch of objects and we determined their orbit from no additional information. So that was really cool. Also, meteor cameras. I know meteor cameras have been used a lot by GMN to look at satellites, and they've been tracking Starlink with them now. And this is something you can do. So don't throw away the satellite data and reentry data because it might be useful. Also, I have an example from Meteor trail radars and reentries. So I got this from Juha yesterday. So here is actually a Meteor trail radar, the C1 radar, observation of dusty plasma after Falcon 9 reentry. So this is just a preliminary plot, but this is sort of the echo from the reentry. So that's really cool. We can actually see reentries in these systems. Okay, so that's enough examples. I just want to finish out with some OSKY 7. You can see it coming in here. And thank you for listening.
Thank you, Daniel. Do you have questions?
Thank you very much. In the past, say IMC in the Palma, the Dr. Abe had a presentation about he observed the spectrum, the mercury, when the Hayabusa 1 re-entry to the Australia. So from the environmental problem standpoint, do you have any comments for the focusing on the materials of the debris, please?
Yes, so I would say the materials are the most important thing to figure out right now. It's like, so there's an interesting, how do you say, question is really, so most re-entry simulations done for space and the technical ones are to see if anything survives to the ground. And maybe less thought is put into like, what's the size distribution of spherules being ejected during ablation? Because that's really gonna tell you if they're just gonna fall to the ground or if they're gonna levitate and start doing chemistry. And we don't really know what that size distribution is. That needs to be much better figured out. And I don't know, maybe there is actually observations you can do to figure that out. And that's sort of why I'm presenting this, because we've seen sort of like the fittings, for example, where we had the sort of light curve fitting, where you calculate how much particles is being generated. Maybe that could be a really cool model adapted for space debris to figure out what the size distribution is. I don't know. We need that kind of expertise to look at it. So, and the data is probably there. So, and if it's not, we have instruments everywhere. We just need to make sure that we see it. I can also mention that the micrometeorite population, so stratospheric flights in the poles to collect particles, they have already been contaminated by space debris. So we can no longer find an uncontaminated sample. Because whenever they collect these samples and do spectroscopy on them, they just start finding like things like hafnium and like stuff that doesn't exist in nature, because it's just everywhere now in the atmosphere already. Yeah.
Other questions?
At the Tau Hercules some years ago, we have also seen persistent trains. They are very slowly, the Tau Hercules, but there are some persistent trains. Is it possible also to see at re-entries persistent trains?
I don't know. I haven't actually collected enough data on reentries to say that. This is sort of the thing that I want to get going, is that whenever this happens, we should save it, because I've seen like 5 videos of reentries. I don't have enough data actually, unfortunately. So, but I think it should be no problem. Yeah.
Okay, let's thank Daniel one more